Select the structure of the first tetrahedral intermediate that is formed in the following reaction. So we can see that we are starting with an ester, and we are reacting this with aqueous acid and heat. So these are acidic hydrolysis conditions. And we are forming a carboxylic acid and an alcohol. So hydrolysis means that you're adding water and that you are cleaving a bond. So the bond that we are breaking is this one here overall. So this portion is becoming our carboxylic acid, and whatever ester we had is becoming the alcohol. So if you had the methyl ester, you're going to form methanol. If this was an ethyl ester, you would form ethanol, and so on. And so we're being asked about the tetrahedral intermediate, the first one that's formed in the reaction. So we want to look at the reaction mechanism in order to answer this. So we want to make sure that we understand what we have to work with, that we have our ester, and that we have this H3O+. So we want to recognize that that means that in solution we have H3O+, which is an acid, and it's probably not a whole lot of H3O+. Usually use an acid catalyst, so you have a small concentration of acid. The majority of the solution is going to be water, and water can function as both a base or a nucleophile, and we will see it doing both in the course of this reaction. And so esters being less reactive of carboxylic acid derivatives, that's why we need an acid catalyst. A less reactive derivative and a weak nucleophile like water would simply result in no reaction. So let's take a look at how the acid catalyzes this reaction. So I'm going to start by redrawing this ester. And so the first step when you have an acid catalyst with one of these carboxylic acid derivatives is you're going to protonate that carbonyl oxygen. So I'm going to draw the H3O+ catalyst. And so the carbonyl oxygen in this first step is going to act as a base and take the proton from the H3O+. And this is a reversible step. And so we'll draw this protonated carbonyl. And so this protonated carbonyl is more reactive than the neutral ester. And so by making the electrophilic carbon more reactive, it can react with a weak nucleophile like water, which is what's going to happen in the next step. So I'm going to draw a water molecule. And we need to understand that water is both a solvent and a reagent, so we basically have a ton of it relative to everything else. So don't worry if you see more than one water molecule appear in this mechanism. So the water is going to attack that carbonyl carbon, and we're going to break the pi bond, pushing the electrons up onto the oxygen. So we're taking this from an sp2 trigonal planar carbon to an sp3 tetrahedral carbon. So this will be what we call the tetrahedral intermediate, and it is the first one that appears in this mechanism. So this is what we're being asked about in this particular problem. So let's go ahead and draw the structure. So once we push those electrons onto the oxygen, it no longer has a positive charge. We still have that methoxy group, and we have added on the water. And both of those hydrogens will still be attached to the water at this stage because the entire molecule is what was acting as the nucleophile. So that means we now have a positive charge on this bottom oxygen. And so this is what we call the tetrahedral intermediate. This is the first one that has formed, so we can take a look at our options, and we can see that this matches B. Okay, so we've got the answer to the question. I'm going to go ahead and finish the mechanism just so we have it. So the next thing that's going to happen, remember we said we can see water appear more than once, is water is going to remove a proton to give us a neutral tetrahedral intermediate. So if you were asked about a neutral tetrahedral intermediate, the next one is the one that you would want to draw. Okay, so we've got the OH on the top, OCH3, and now just OH on the bottom, so this is neutral. And what we need to do to get to these products is we need to get this methoxy group being a good leaving group. It is absolutely not going to leave as OCH3-, which is a relatively strong base in acidic solution. So we need to protonate this to make it into a good leaving group. So we can use that H3O+. right? And so notice we're constantly using H3O+ and regenerating it. So that's why we have it in solution. So we can protonate that oxygen. And so we're just trying to set that OCH3 up to be a better leaving group. And so now being protonated, it can leave as a neutral molecule, right? So we can use either one of these oxygen's electrons to push down. So I'm gonna go from the top oxygen, but it doesn't actually matter. And so we can bring these electrons down to reform the pi bond and push off that leaving group. So we can see where we're getting the methanol from. We're pushing it off and cleaving that bond right here. So that's gonna give us, the arrow should be going the other way. So we're forming methanol there. And we've also got the protonated carboxylic acid, so really close to the final product here. And we can use another molecule of water to remove this proton. And then we will have both of the products that we were given. So we can see where they are both coming from.